Okay. So then, okay. Great. Thank you, everyone. And thank you, everyone, for joining us, and good afternoon. It gives me great pleasure today in introducing Dr. Professor Nima Rahbar from the Civil and Environmental Engineering Department at WPI. We've had Professor Rahbar, if I'm not mistaken, is our first in-university, in-person speaker to talk to us this semester. From outside the material sciences department. So today he'd be talking to us about carbon negative healing enzymatic construction material, which is also one of his main research interests as of now. I'll just. Oh. So Professor Rahbar received his a PhD in mechanics, materials, and structures from the Department of Civil Engineering at Princeton, and joined WPI in August 2012 as assistant professor after starting his career at Dartmouth. He has a bachelor's degree from Sharif University of Technology, and also a master's degree from Northeastern. He is currently associate professor of civil engineering, and his research interests are bio-inspired design of materials, focusing on thermal and mechanical properties. He has won many awards, of which some of them are listed: the NSF Career Award in 2012, the TMS Young Leaders Award in 2013, the Air Force Summer Faculty Fellowship Award in 2013, the Outstanding Reviewer for the ASCE in both 2015 and 2016, the Outstanding Junior Faculty Award from Sigma Chi in 2020, and the ONR Summer Senior Faculty Fellowship in 2022. He has also been a visiting associate professor at the Civil and Environmental Engineering departments at both MIT and Cornell in 2020. His latest work, of course, as mentioned, is focused on working on enzymatic self-healing concrete and negative emission construction materials. And he will be talking about that today. And with that, I would like to hand it to Professor Rahbar.
Thank you. Thank you very much, Alita, for the lovely introduction. Very nice of you. Do I have to stand here for the microphone, or I can move around? I'm a very jittery guy. I don't think I can stand up. You're probably actually I shout, so that's good. It's great to see you guys again. I think I gave one of these talks in materials. I was just telling Adam a few years back, so it's again good to be connecting with our own students. My lab at WPI actually has students from mechanical, bio, and civil, and the main focus is what can be learned from nature proof, which is designed through the process of natural selection and evolution. So we started looking at some model materials such as natural tooth when I was a PhD student. In the 2012, when I came here, we were working on inspiration from cartilage to make gel-like material. Was very tough. A major work in my lab has been focused on bamboo and inspiration from bamboo, which is a grass, it's not a tree. It grows really fast. Strength to weight ratio, stiffness to weight ratio, which what material science are interested in, are higher than steel and concrete. So we want to see why is this material so great. I had two students who actually worked on that. My second PhD student was actually in mechanical, Sinab Y. And actually, in collaboration with Stephen Van Dessel, who's in the room, we have been interested in looking at inspiration from animals who can survive really high temperature at the bottom of the ocean. We were trying to see what is so special about the structure of their lipids. What can we learn there to design thermal diets, thermal thin films that they can be at thermal diets that temperatures can go one way and doesn't go the other way. But the story that I want to tell today is mostly on this inspiration from my major work, which was the subject of my career stuff, and that's inspiration from nacre, or inner layer of abalone shell. I want to say that the other half of my lab are people who are working on additive manufacturing and metals, who are not here today. I don't see them. And this is the work that we do with Professor Mishra and Wooly on cold spray and high entropy alloys. These are, if you're interested in, these are alloys with gigapascal strength and massive toughness. So they're really interesting materials, but that could be subject of another talk by itself. As I said, in 2012, when I came here, my whole goal after grad school was bigger, faster, stronger. I want to make bulletproof jackets so that the bullet doesn't go through, ceramics who are tough. But as I worked after my sort of 16, 17 tenure, I changed that attitude and tried to focus on the challenge of our time. Actually, this slide, I just stole it from my department chair yesterday, who posted this in the faculty meeting and said, say goodbye to 1.5 degrees C. So the challenge of our time really is climate change, right? So I want to tell you the story of how do we get to that. And just another note, I also stole this from my department chair a while back, that even if you cover all these areas by photovoltaics, it would still not be enough. And this is actually based on 1.5 degree. If you want to attack the problem of climate change. So the challenge of our time really is figuring out how can we reduce carbon. This is a tough and interesting problem. And I was actually listening to one of these nature shows by David Attenborough, which you guys have seen with my children. You know, these things that it talks about nature. And David was saying, David Attenborough, that most people are very much concerned about Ebolas and COVIDs, but the actual problem is actually climate change. It really is a much larger problem. So it requires a lot of attention. So as Aditya was saying, my training is all in structural engineering. I'm a guy who still teach kids how to design buildings and bridges. So in my heart, I like to make structures that carry loads. And in the story to getting to these new type of materials, another issue that came up is the story of durability of structural materials. So this is, you guys all remember this, right? This is one of the most amazing, in a negative sense, failures that has happened. This was last year in Florida. Remember, a building just completely collapsed. So I actually teach reinforced concrete right now, which I see a few of my students here, right? And I always tell them in class, if you follow basics of code, just basics of it, this should never happen, even in a 50-year, 100-year thing. We design things you see a crack here, you see a crack there, you see some deformations, but things should never fail this way. So we have the issue of climate change, which is really interesting. We also, our infrastructure materials are not as durable, right? There's a bill just passed. Our structures look old and feeble. And you can see cases like this, that and a massive building actually completely failing. And I was in Florida in February, went to see my uncle. I was driving by Miami Beach. There are buildings, if you guys have been this, they're just 60-story, 70-story, 80-story building, one after another. Many of those have to be evacuated. In fact, many of them has already started evacuation. This is a serious problem. Buildings on Boston coast, also the same thing. So what's the need? So need is, concrete is a major construction material, most used material in the world, actually. It by itself contributes about 9% of global emission. It's a big deal. Why? Because concrete is a powder that they put the energy into it to make it. And then as you mix it with water, it becomes this hard rock, right? So it's very energy intensive, not super expensive, incredibly interesting material. It's not going to go away like oil, but it has an energy issue. We have to figure that out. So 30% of that relates to replacement and repair and all that. So an alternative to durable concrete or durable illustration material, it's needed. There's been numerous calls the past few years on in agencies. They're all asking literally durable construction material, all sorts, because the way we have done for the last 200 years or maybe 2,000 years of making concrete, which is limestone reverse, we have to come up with ways to not short circuit. So concrete is a short circle metamorphism, right? You want to make rocks very quickly, and it's really good. But the problem is, first of all, it's energy intensive. Second, it's also a lot of waste. We make about the size of, this is I remember from my undergrad days or grad students days. In 97, 98 report was saying we make about the size of Paris concrete waste every year, a meter of Paris, right? So this also adds to the system, and waste is another really important aspect of this. So this is a video that World Economic Forum made it for us. Shuei sent this to me when we were doing this. Oh, it has a sound too, but it's not. I don't know where the sound is. Anyway, this was our, they made this video for us. I think it's cool. I always think is attractive to the undergrads. So sort of summarizing what I'm saying into what we thought we can do to what we have done to came up with this idea of a self-healing concrete. If you Google it, it's on YouTube and you can take a look at it. It's pretty cool. But I want to tell you today what the story of how did we came up to this idea of using an enzyme to create a self-healing sort of a durable concrete. Okay, let me just go through it quickly. So when I came here, as I said, the focus was bigger, faster, better. And we want in material science, the holy grail is, can I figure out materials who are light and tough? And light materials are, ceramics is the one, but most ceramics are not tough. Then Tony Evans, who was at Princeton, came up with this brilliant idea of founding this material called nacre, NaCr, the inner layer of abalone shell, that is 95% ceramics, only 5% protein, but its toughness is 3 orders of magnitude higher than just if you just have pure ceramics. That sounds like magical, right? By the way, today, and the obituary of Tony Evans in Royal Society came out by John Hutchinson. For all material students, you need to read it. Tony Evans is the greatest material scientist I know. So just Google it, Royal Society of England, I assume. And Tony Evans, look at it. It's really interesting. That's how I copied the picture actually from. I went there as a student, and the focus of Tony was, what can we understand from this to copy it? So when I became faculty, I started really working on this. And the idea is, what is so special about naked that has this incredible property? By just adding 5% protein, you can create material that's 3,000 times tougher. So this is the work that was started by my PhD student, Sina A. And we thought the mechanics of nacre is, you have this brick and mortar structure with the tablets, and we have these pillars who sort of at nanoscale bind these two plates together. The yellow stuff is the protein that bonds hold the whole system together. And if you build this, I'm jumping to a lot of slide and simulations here. So you can build mechanics models of this, and you can see that this huge enhancement in toughness coming from this aspect of distributed deformation through the system. In regular ceramics, you have one crack that zips through, right? When you have a brick and mortar system with these asperities, I forgot to mention, they have asperities now. It is the model of a unit cell of the nacre. You have the asperities, the pillars, they break, they move on top of each other, so you consume energy. So you have a system that is quite tough. So if you are interested, take a look at this paper at Royal Society Interface that we say, look, our model sort of predicts that the optimal ratio for the plates are about 10, and these are different simulations for the platelets length to thickness ratio. You can get different behavior based on the tweaking in your model. You make these models so you can design materials with a certain property. The interesting thing that we discovered, what I thought our contribution to the field was, this beta 1 of 1%, 2%, 4% is the distribution of these pillars. So my assumption was at the time that, let me just go back quickly. In order for these properties to work, if you just print a material like this with these properties, you will not get that toughness. The reason this is so incredible, because the proteins, which are the yellow stuff in here, they behave really incredibly. So if you just pull a one molecular protein, the strengths are in pascals. They're really weak, right? In fact, there's an experiment by Paul Hansman who actually did that. But we thought because of the charges, the plates are negatively charged, they push the protein in nanoscale, that gap between them is about 20 nano. And that would enhance the properties of protein to a level that, so the organic matrix is about 4 GPa, which then, and now everything works out. All the composite stuff would work out. And there is a cool message here for some of the younger students. My own students don't even remember this. We wrote this paper, submitted to a very big journal, and they said, go to hell. It's not true. So I said, okay, fine. Submitted to the Royal Society interface, got accepted. And a few years later, PNAS article, quantifying the role of mineral bridges on the fracture resistance of nickel-like composites, showed exactly what we did. And in fact, this gentleman, Andre Studart, who's an outstanding material scientist in ETH, he called me and said, Nima, we actually read your paper and we did the experiment to exactly shows that. So I was a sprinter in college. Science is not a sprinting, is marathon. Just keep at it. Things people will eventually believe you. Anyway, my goal over there was, if I understand nature so well, if I understand the microstructure, then I can make materials very tough. And in fact, we did. So I jumped through a bunch of slides in here because I wanted an overall story. Sina, actually, this student, PhD student who was in this field, made composite like nature with alumina, with polyurethane and another polymer which I forgot. But we got toughness close to nature, although there's a bit of a cheating involved in here. Naked is 95% ceramics. Nobody has ever been able to, with the method of freeze casting, we were making this in our cave and hall building. Nobody has been even been close to making a composite that is 95% ceramics and 5% protein. The best we can come up with about 60%. 60% ceramics, 40% polymers, and then you get very nice behavior. But getting it to 90%, because this is biochemical growth. This is an evolutionary process, very, very complex. So, but we thought this is a promising field. The simulation stuff is just too long, takes forever. So with Sina, we figured out this mechanics framework, which again, I just jumped through some of the slides, but you guys have all seen the shear lag theory in your composite classes, right? This is basically shear lag. Is all this fancy math really means you have a unit cell, you have plates one or half plates of 1, 2, 3, 4. If you write balance of forces, that equation 1 to 4 is just balance of forces for those plates, just presented in a fancy way, and the boundary condition. So you don't have to go through all the finite elements, nonlinear stuff, because it takes forever to converge and all that. So we came up with this mechanics framework of just getting equations for stiffness, strength, and toughness, so we can use for composite design. I had another student, Arvand, who actually had materials background. He did simulation, molecular dynamic simulation of the protein in the gaps. So remember I was saying the reason the proteins are in the GPA strength level, because they're in that 20 gap. So he did simulation for 30 gap, 30 angstrom, 37, 47. So try to study these and actually showed that the density of the protein in the boundaries goes higher. So you have enhancement in the strength, and as gaps closes. Think about it. You have a plate of a spaghetti. As you push them too hard together, it's hard to pull one out, right? I mean, our comparisons are mechanical, but these are mostly about the charges. Actually, this work also is now shown. There's an MIT group who works on fluid. They show the exact same thing on the boundaries. When you have charges in small gaps, you have enhancement in density. So this was sort of justification of, as you can see, the proteins stiffness and strength goes up as you confine them. It's called the nano confinement effect. So we plug that into our sort of a shear lag formulation. This nasty stuff really means if you have the two plates and you have the protein in between, or the material design system, this modulus of the matrix is enhanced by this ratio. At the vicinity of the plate, you are stiffer and stronger. So kappa means the enhancement in modulus, just see just normalized thickness. So it wants to say, as you have higher kappas, your stiffness of the composite just increase and then plateaus. And here, the stiffness of the composite normalized as a function of the thickness of, obviously the higher thickness creates higher stiffnesses. But you can use this equation published in composite B to design composites who have these brick and mortar type structure. This really long equation is the strength of composite. Here is and in shear. You can compute, or look at the graphs basically. You can compute the strength of composite normalized as a function of kappa, and Kc means the thickness or the weight, the length of the plates. These are nice sort of materials equation you can use to design it. So here's a summary of elastic modulus, toughness, and strength, published in Composite B, actually last year finally came out. I think these are really nice work in terms of if you want to design something, you want a certain toughness, a certain strength, and you have a brick and mortar structure, you can use this to sort of design your composite. But the point I wanted to mention in here is, I believe for native. So if you go, I'm sure you guys have done this. If you go to nowadays to any mechanics or material science conference, there is at least 4 or 5 sessions on Naker. And people are still struggling to fully understand. What I strongly believe is those pillars, those nanoscale stuff in between them, create the confinement for the polymers or the proteins to get to that level of strength. And these are what's trying to show that these graphs are ones are with bridges and without the bridges. So if you're interested, take a look at the paper. Anyway, going back to our story of self-healing stuff. So we studied Naker. Like, for example, I had a student, Habibe, who started master work as, what if I change the angle of the interlocking between the plates, printed composite, made simulation, and figured out you can be too pointy, sort of too, she calls those bow tie structure. Bow tie is not good because it becomes brittle, but exaggerated wavy. So you have a lot of interlocking. You create a lot of energy when you want to pull out the thing. So you have a very tough system. So inspired by that, another master student at the time I had, Jessica Rosewitz, said that, well, what if we reinforce concrete that I teach the students in class today? We always have rebars, and then we design how much reinforcement we need to design the composite section, right? Jessica's idea was, what if we print these Naker-like brick and mortar, or auxetic, means negative Poisson ratio, right? You guys know what a negative Poisson ratio is. Most materials have positive negative Poisson ratio, some have negative, meaning as I compress it, it gets thinner. So printed a negative Poisson ratio polymer and fill it up with cement with the same ratio. So I have the same ratio of a basically just fiber reinforced or design microstructure polymer with the same amount. And you can see that we have about 30% increase in specific strength of the system. So actually my student right now trying to do the same thing with steel to show that for a regular reinforced concrete section with 2 rebars, we have this much strength. If we design the microstructure with a negative Poisson ratio that we do, how much enhancement you have. Okay, great. I was very much interested in durability of cement and enhancing the recovery. So I had a student who actually started his master here, went to Iran and couldn't come back. So finished his PhD in Southampton, amazingly. But she was interested in understanding the role of fiber reinforced cement because it's similar to Naker. We worked on this for many years and actually didn't really work out. So going back to the need, we thought we have to do something to solve this problem, creating a replacement for cement of sort, or enhancing at least the durability of cement. So in 2015, I started with a student working a lot on this concept of microbial self-healing of concrete. The idea is you put bacteria, which are like long capsules inside the cement. They are negatively charged. So as you, when you have CO2 into the system, means there's the crack in the system. You have calcium inside the concrete. With the CO2 will be a reaction, and the crystals will grow from the surface of the bacteria, and then you will heal cracks. In fact, it's a brilliant idea. Came up with the gentleman with the name of Yonkers in Netherlands. Came up with the idea. Who was a biologist. At the time, I think in 2010, MIT president Chuck West at the time said, this is among the top 3 ideas of the decade. And I think it's a really brilliant idea. It has a few problems though. Actually, we started working on this, and the problems were the following. One was the rate of healing. So you can see here, there's a crack. I mean, as you can see, the white stuff is the crystal, they're growing. So this is like almost like a 28 days, and the width is really limited to about 10 microns. But the process is extremely slow. You have to use bacterias. It's very hard, actually, road grants that I realize people don't like to have their house or bridge fixed with a bacteria or the microbes. They're very scared. And it's also a bit smelly. Actually, not a bit, a lot smelly. It's essentially, this is a mold in your basement. Bacillus subtilis is what they use, is essentially mold in the basement. So, and because of its very slowness, the width of the crack healing is actually quite small. It's about 10 microns. They say it's about 100, but it's about 10. So at WPI, I was playing soccer on Tuesdays, which some of the students do. Actually, Yan Wang always comes and plays with us. So I had this colleague, Susanna Scarlata, that I once asked her, look, and I like bio-inspiration. All of my work is about bio-inspiration. I was like, who does the transfer of CO2 in our body? Because I really wanted to make a reaction with CO2 very quickly. And she was like, oh, that's easy. That's an enzyme called carbonic anhydrase. So that's how I got interested in enzyme, and working with Suzanne was brilliant. Enzymes are really interesting for us who are in more of a structural side of material science. They are catalysts, biological catalysts. Carbonic anhydrase make a reaction that without carbonic anhydrase, as a not being existed as a catalyst, it takes 2.3 billion years. So every millisecond in your body is a reaction that is expedited by 2.3 billion years, evolutionary, right? What happens is you inhale oxygen, goes to your blood, you take it to the cells, they take the oxygen, they burn it, it becomes CO2, they pass the CO2 to your blood and goes and you exhale it out, right? This fast transfer of CO2 is done by carbonic anhydrase, or also exists in many other places in kidney, lungs, and all that. So what we thought is, I don't know why the quality of this image is like this. The idea was when we use carbonic anhydrase inside concrete, we place it in, as you open up a surface that now have access to calcium and CO2, the carbonic anhydrase provides bicarbonate ions that reacts with calcium, and you deposit calcium carbonate. So when a crack opens up, as you can see in here, I don't know why this image is so bad, but the calcium carbonate crystals are getting deposited and fill up the crack. Here's an interface of the concrete substrate and the crystal growth on the surface. Here is a sample that Jessica healed. This is not self-healing, but this is a system that is healed with enzyme, with the sizes are humongous. This is 12 millimeters by maybe 5 or 6. I forgot exactly. Shui remembers that. So enzymes do this incredible reaction, and they are, the reason you take vitamins, because you can make vitamins. Vitamins you have to absorb it to add it. We can have the fruits and absorb that, but we cannot replicate them. They are evolutionary processes. They're evolutionary molecules. Really interesting. Carbonic anhydrase has this pocket that very low energetically provide this bicarbonate ion that makes reaction with this is calcium. I don't know why it says Ca. Capital should be lowercase a. With things. So here is some images of the process. You have the surface of the cement, and as this is self-healing stuff. This is cement with the calcium, with the carbonic anhydrase in it. As you add water, this is Jessica's experiment. You can see crystals are growing, and this is the image that you saw before. They're growing through the gaps and then fill it up. And remember, things will not overflow. It's not a cake, because when you cover up the surface, then you don't have access to CO2 anymore. So the process just stops, right? Here is a video that Shui made of here's a sample with a notch, and actually randomly there's a little hole in it too. And this is inside the solution, and it's going right inside the solution. And as you bubble the CO2, so enzyme is the engine. And as we provide more and more fuel, which is the CO2, remember, it also needs calcium. And then the reaction will keep going to the right side, and then you deposit crystals. So here is, as you can see, the crystals are depositing on the notch and the hole, and it just keeps going. I think this is I forgot, this is 24 hours process. Yeah, 6 hours. And then you can see the cracks are filled at 3 and 1.5 millimeters very quickly. So SEM images of a surface that the knife, Jessica sort of scratched it, and then crystals will grow. So we have evidence quite nicely. Here's a test that we did, because concrete community very much likes to know about penetration. So this is a 3 millimeter and a 4 millimeter hole that we, with enzymes and crystals, fill it up, and water stays there for hours. It's just getting evaporated. It doesn't go through the system. I believe we have also done this with alcohol, and it works. Here is a graphs on sort of a mechanical property. So you have control samples with a sort of circular hole in it and elliptical flaws. And as you can see, for circular notches are a little notorious for regaining strength in ceramics, but we did it. So we get some enhancement quite a bit when we fill it up. Oh, by the way, we compare control with regular, quick fit that you buy in Home Depot to fill up the holes and notches. And for the case of actually a crack-like elliptical flaw, you can see this is a control sample. This is with the mortar available in the market. And this is a massive hole, by the way, 12 by 3 millimeters. And for our case of fill it up, for 47 samples, by the way, this is almost 100% regaining of strength. So in repair works really nicely. We're very confident. In fact, we are just in the process of getting the data together with my two students and submit it for a license in New York State and in California. This is enhancement in tensile strength and fracture toughness. It's about 20% enhancement in a system that when you make the concrete with enzyme. It's not really much, but you have some enhancement, because the bond between crystals and cement is not super strong, but it's just weak. You add a little bit, but not much. In the concrete community, if you want to sort of prove your durability, the standard test is something called RCPT test, rapid coiled ion transport test. My student Jessica, who started this work, who's now, by the way, is Professor Jessica Roosevelt in our department, came up with this experiment that called dye test. And in here, so she made these cylinders and fill up the top of the cylinder with a dye. And for the control sample versus the enzyme sample, you can see the progressive dye is far less, which means you have less porosity, less transfer of ion, and more durable reinforced concrete system. This is a creative method. Actually, now my new student Sarah is trying to write this as a standard technique for measuring the durability of concrete. So that's one way of showing that our enzyme-made cement is more durable. Another way, by this technique of, as I said, rapid chloride permeability test or penetration test. As you can see, in this method, what you do, you make a disc of concrete, and then you put it between the two charges. You pass a current through it, and you measure the ions. So our system is always this is a control system, and this is sort of carbonic anhydrase modified cement. Is always less. It's almost actually it's just one set of data. Our new set of data is even better than this. It's about half. You pass you block the transfer of ions more and more. Problem with this test is extremely finicky. It depends on the purity of the cement and what you have. So this is it's not super reliable, but it also works for us. This is another test that my student Shui Wang did on. This is a very reliable method. This is called accelerated corrosion. So you have a bar in a concrete cylinder, and then you drive the ions very strongly by current into it. And as you can see, for like a 7-day or a 14-day or 28-day, our system does cracks a lot later than a control sample who's made just a regular concrete versus the enzyme reinforced concrete. We also have done tests on thermal properties of our system. So which is sort of expected, if those strength regaining that I was talking about, if you repeat those tests at the -20 or 50 C for a control circular flaw or elliptical flaw, the strength enhancement is almost complete. But this is not that we make the system at -20. You make a system and test it at -20 or 50 C. So it works nicely. So overall, what is our approach to here is you have the MICP, this microbially induced crystal precipitation method, the bacteria-based. This system, the health is not really known. CO2 production is much lower. This is the main difference, really. They use oxygen. So our system actually use CO2. Crystal production is about 4-fold higher because bacteria has to secrete a bit of an enzyme to do this reaction. We actually flood the whole thing with enzyme. So it's extremely fast. And there's no smell or harmful, it's just enzyme, which is everywhere. The most important issue, maybe in my opinion, is also cost. So our cost is about 20%, maybe $120, $130 a cubic yard concrete, which is about 100. But microbial concrete is about $1,000. So it's really expensive because it's hard to work with. Now, on the self-healing side, here is a video that Shui made of a sample with a record 1 millimeter flaw width. And so he puts it down. You have to, either in the microbial system, in our system, you have to provide some calcium, remember, because you can't create materials out of nothing. You have to have calcium and then CO2 in the air to make the reaction and deposit the crystals. So here, this is, as far as we know, in 24 hours, we can fill it up a crack that is about a 1 millimeter width. Very quickly, we provide some calcium and then we blow CO2. I mean, we provide a lot of CO2. If you leave it outside, it takes about maybe a week or two, 10 days at least, to really cover up. But when you blow CO2, it's a lot faster. So the idea is if you have your bridge deck, you spray our solution, sit a little bit, and then you blow the CO2 like a leaf blower, and then the crystals will grow and cover up the small pores. Now, going back to challenge of our time, long introduction, is now what can I do to help the climate change? Obviously, making concrete durable definitely helps, but can I replace altogether the concrete? And that's how we came up with the idea of enzymatic self-healing construction materials, called ECM. And here's what Shuey made as a representative for St. Louis Arch, but it more looks like more like a McDonald's arch. And that's his try. If you mix two of them, it becomes McDonald's arch. This is a really, really active field. You won't believe this. Almost every institution now is having a center, or is going to having a center, or is focusing on the next generation construction materials that are not as carbon enhancing as concrete. So the leading group that we know is a group in Colorado State, in University of Colorado, Boulder, who trying to do the same thing, making materials with the bacteria. So they don't have self-healing data, and their strength is about 3.84 MPa, which is interesting because you can still, this is a material that doesn't have any cement. You bond the particles together, so it's a nice thing using. There are some fungi based, by the way. Those are not very strong. But his system of using bacteria is decent. It's about 4 MPa, sensitive to water a bit, but it has a foul odor. Actually, I've asked he's a student, and this is very terrible. It's hard to stand against it. So same stuff as the other one, low. So we thought what we can do is we have our enzyme with the solution. We put the sand particles in it, and we add an initial polymer that holds the stuff together, sort of like a scaffolding, like a regular concrete, you have a scaffold. And as we have the scaffolding, as the CA is there, grows crystals will sit on the scaffolding and they grow, and we can make sort of a nice, decent, dense material. Here is the goal is to have a dense, heavy, good, strong material. And then we also have self-healing because enzyme is in it. If it's a crack, you blow CO2 and things will grow if you have calcium, so you can rebuild it. So here is another video that people like, again, made by Shui, my star student. Where is the music? What happens? This has a, oh, there it is. WPI said we cannot put the music on the website because that's copyright. So you can see he puts the solution, and then we have, it's the early days that we did, has a strength of about 10 MPa, at least 2.5 times what's available. It's really simple. You mix it, you blow the CO2, and it cures. If it's cracked, CO2 aeration, again, it has again decent self-healing properties. And the beauty of, I think the most interesting part is, a cubic yard of concrete is about 40 pounds of CO2 emission, and ours is minus 18 pounds of CO2. Here is the details of the work. So weight gain, we started by having just maybe base. We thought base is enough to do this. We have base and calcium, base and enzyme and calcium, just the enzyme. But the sort of soup, the recipe that we have is sort of creates the densest, the highest gain of CO2 in the system. So this is the material. Imagine it has CO2 in it as the process is made. So these are nice SEM images that Shui made from GL, means just gelatin with calcium, gelatin with base, and the whole ECM, which is gelatin, calcium, and enzyme. And you can see that the red is the EDX of calcium, quite a bit dense. It's very decent. The FTIRs and the XRD shows that our calcite So here is a really nice image that Shuai made, 0 minutes, 5 minutes, and 10 minutes, optical microscope and SEMs that you can see the sands particle next to each other, and we have the scaffolding. Over the scaffolding, crystals are growing and bonding. Here is another one, 0, 5, and 2. It's pretty quick. In 20 minutes, we sort of things grow and gel and build this stuff together. This is quite nice. This is a strength test for different, as I said, recipes, and ECM is the best. We have decent fracture strength. This is, remember, concrete and these ceramics will work in compression, not in tension. So we have some fracture tests, but we don't expect much from these things, although it's not been too bad. Actually, a specific toughness is actually pretty decent. So the mechanism really is, the failure mechanism are just particle debonding, and the bridges are breaking. So this is a work that published in Matter. So this is an ECM strength at the time, strength about 9, 10. We add, this is the tannin. Tannin is what we have in wine, by the way. We thought this would help. It's not so great, but we added glutaraldehyde, and we got about 12, which has a very decent strength. So this is a world record in an alternative material to concrete. There's another field called geopolymers. You can use those things, but those are fluctuating, and you can really, this is easy recipe, very stable, and it would give you this decent 12 MPa. We have also done in the paper, if you're interested, I'm not going to go through, there's a lot of stuff in here. We model how the bridges will grow, and actually we borrowed this from old material science, like basically crystal growths in metallurgy, and we model also the lines. The solid line is the model, the diffusion-based model that we have, and the red is the measurements, so we can predict it nicely. And the nice part is also we have self-healing, as I was describing, as the video was showing. This is an ECM with a crack, and as we blow CO2, we reestablish some of the bridges. So here's the experiment, extensive experiment that Shuai did, that we have about 6 cycles of self-healing, although we don't go back to the 50 load that we have, about to establish is about 25. But you can do 6 cycles of self-healing, which is, I think, it's quite nice. I don't know any other alternative material we can do this. What we later on, 5 minutes. I'll wrap it up in 2 minutes. Sorry. Just quickly, we thought we're working with the Army, and one of the goals is, can you make these materials for us in Mars or in a distant island? So we thought adding a tiny bit of nanoparticles in it and cure the stuff with laser. So this is, I'm going to go through them very quickly. So we can cure the material with laser very quickly. I have 2 undergrads here, so now trying to actually use this method to actually heat up buildings as well. So we can cure things very quickly. So look, here's the sample is inside a freezer of -20. As we add laser, shine the laser to it, it goes about 60. So it cures very quickly. The idea is if your system cracks, you can shine the laser like a little laser pointer. Oh, it's a very, very weak laser. It's a laser of 3 watts. So you can sort of re-heal the system pretty quickly. These are simulations of the process. But here Shuai made some CTs that shows that we rebuild the bridges with the laser. So here the laser is basically replacing the curing by an oven. If you're stuck somewhere, you can use that. It's also quite not energy intensive. It's very smart with energy. So regaining a strength similar to the stuff, it works fine. And in terms of Ashby chart, so embodied energy of this material is negative. So in terms of embodied CO2, not the energy. So we actually put CO2 into the system, so it's carbon negative. I'm not going to go through this, but if you're interested in also the other side of my life is simulation, we use a technique called semi grand canonical Monte Carlo simulation to do fracture. There's no time, but I can, if you're interested, you can come and talk to me about this. We do actually grand canonical, but instead of removing particles, we're removing bonds to simulate things that are really complex in fracture. So I'll go through this. Oops, I stopped here. Thanking NSF for awards, multiple. We had some money from World Bank. Some of the students were visiting. The very first funding we got for this work was from Math Catalyst. My students, Jessica, Shuai, Sina, and Habibe. Clara is an undergrad who works with us. There are a bunch of REUs who have worked throughout the years. Thank you. I am happy to. Yeah.
Thank you, Professor Rahbar. We still have time for question answers. So does anybody have any questions?
See to do this stuff very quickly. I also talk fast, so it doesn't help. Yes.
Jason?
What are the upfront like production costs of using this?
Excellent question. So we when I first presented this, concrete people like, carbonic anhydrase is very expensive. Actually, that's not true. We actually started working with a company in Northern California and now switched to another company in Florida, who these guys have techniques who can make this out of bovine, out of cows, very inexpensively. So, by the way, remember, we need a really tiny amount of enzyme because these are cows, they're not getting consumed, right? So the portions are very, very small. But that's basically the only cost, as long as you can make it cheaply, which we can make it cheaply in large volume, not smaller. For a smaller, we actually have to buy it from the Sigma, which is quite expensive. But in large volumes, you can reduce the cost.
So that begs the question then, right? You only need a very small amount of enzyme, but that's because you are providing the material to heal the crack externally. And in a compressive situation like this, how often do you have access to be able to diffuse the materials you need into a crack to be able to heal something that's an internal flaw?
Well, there's,
for example, like, I think all the buildings you talked about at the beginning, the ones in Florida specifically, all of those are rebar rusting internally inside of it, creating an expansion, which is then creating a crack. Right, that's what those buildings are failing from. It's corrosion-based expansion along the rebar, which causes the crack.
The fundamental issue that you're missing is this.
Yeah.
Any failure happens due to a crack. Do you agree? Crack has to open.
Yeah.
The moment you open, you have access to CO2, enzymes are there, you have calcium, you heal the stuff. The self-healing happens in what way? You have to open a nano thing in the beginning that becomes a large thing, right? As you open it up, look, if you don't have access to CO2, if the flaw is inside and it's not growing, yes, I can have access and it's fine, it's just there.
Well, it's the CO2, yes. Like you can diffuse gas through very, very small cracks. So CO2 access is one thing, but you said you also needed calcium. You needed to diffuse calcium through and into that in order to heal it as well, right?
Well, there's two things. You either want to repair stuff. For repair, you have to inject stuff, right?
Yeah.
Things like the Florida thing, failures, by the way, 99% of failure starts from the surface, right? That's just basically what happens. So on this, if you open up something even at the nano scale, you have access to CO2, there's calcium there, and you will repair it. You see what I'm saying?
Okay.
So if you have a flaw inside that is, let's say, it's this big, but it doesn't have access, it's not growing, so it's not a problem. It's just there. Right? It's not like this big. But you know what I'm talking about?
Yeah.
The beauty of this method, which is that's not actually our contribution. It's coming from the NYCP.
Right.
When you open up access to CO2, then these things will grow.
Okay.
Does that make sense?
Yeah, I'm coming from the world of metallurgy where internal flaws, initiation and fatigue, compressive and
fatigue is 99% surface stuff.
In low cycle in the metals, yes, but in high cycle, very high cycle fatigue and the very low
Inside,
it's all internal.
But this stuff is not fatigue in civil structures is various.
Right. It's
So
different, especially for concrete.
right.
But yeah, I think the thing about the
But even for those inside,
Yeah.
if I'm opening up inside of concrete, there's always the time we have calcium. So if you have to access to CO2, somehow it has to get
Right, well,
in.
gas diffusion through a crack is
it's easier.
It's a given, right? Yeah, it's the other larger structural material diffusing into the crack that I was a little bit more
Right.
curious about whether that would actually work in the long run
Right.
or not. And the nice thing about this technique is you actually don't have to necessarily speed it up because you're all outside structures, like you said.
Right.
You could just leave the solution on the structure for a period of weeks or months.
And just look,
You don't
exactly.
need to
I'm
actually
being there.
accelerate
All fluid.
necessarily.
Yeah.
Yeah.
Sorry.
So just to add to this discussion, I mean, it's a proof of concept, right?
Right.
That's
not
works.
obvious.
Yes.
So you don't go from a research concept to a practical solution for. the-
And one shot. Yeah.
In one step. Right?
Yeah.
So I mean, I
Absolutely.
agree with both of you, right? But the sense is, it has to be a progressive.
Absolutely. One thing I didn't mention is we had this work on record-breaking materials, right? On carbon negative. One thing the Colorado people, and we don't mention, is it's very sensitive to moisture, right? If you leave these things in water for a while, it will disintegrate. So actually now, I don't want to present it because we just filed the patent. We now have a new technique, as Tar was saying, and these things are step by step, right? Now we have a technique that actually is quite stable in water for hours, and with a 15 MPa strength. Hopefully the next year I can present that, but that's our latest achievement. But he's a spot on. I mean, these are just, techniques that we just little by little have to add to it.
So yeah, you can't go from this.
You cannot. Believe me.
It's
It's not, yeah. And there's so many levels of things involved in the fluid. I just put it as an example of durability and corrosion, but there's so many things going on there.
The question from the Zoom chat, does this self-repair mechanism work for concrete underwater, like a bridge substructure where there's limited CO2?
I'm sorry. I'm just trying to think this. Say again. Does it work under the water?
Work underwater, concrete bridge substructure where there's limited CO2?
Underwater is harder, to be honest.
Okay.
One thing is it's not about the enzyme, it's sort of mobilized, a small molecule is there, it's just the calcium. Right? It requires some time to harden. So most of the underwater stuff that I know you need, by the way, we don't want to use polymer for repair because polymer is a different material than concrete, different modulus, different thermal properties. Eventually you have an interface, so it's actually worse. So that's the whole I forgot to mention, they want to use epoxy. But on the water, you have to use stuff like a quickly curing. That's the problem. Unless you come up with a way that you can hold the system there for a while. But yes, that's a really decent question. The reason, by the way, this also again not coming from us, came from the microbial people. The reason we always want to have calcium carbonate because it has the same thermal and material properties and concrete. That's the real interesting part. It's almost no interface.
Anyone have any other questions? Any
Anything
more
else?
questions? All right, if
Great,
not,
thank you.
then thank you so much. Oh, that's fine. That's
Just close this, right?
thank you, Professor Rahbar.
Oh, my pleasure. Was it interesting for the
Of course.
materials community
Yeah.
thing? Okay.